This is Lab 4, Oscillations. The objective of this lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on a spring. This lab begins with using Tracker to extract the position data of the mass in the given video. Using the position data extracted from Tracker, an observed model is constructed. We then construct a computational model of the motion using physics principles which will be discussed later. With the two models obtained, we compare the predicted motion and the observed motion of the mass on the same graph. We also plot the energy changes computed in the model. These energy changes include the change in kinetic energy, gravitational potential energy, spring potential energy, and total energy. The graph here displays the comparison of the observed model and the predicted model. This was constructed using the calculated forces, spring constant, and length of the spring at different times. The second graph is a plot of all the energy changes mentioned earlier. As seen by the yellow plot, the total energy change was very close to zero during the mass's motion. This lab once again utilizes the fundamental principle of physics, which is Newton's second law. The first equation relates the final velocity to the initial velocity, and the second equation relates the final position to the initial position. Both will be used in the code that constructs the computational model. The second principle is the energy principle. This states that the change in energy of the system is equal to the work done on the system. The values on the left are the values given to us. These include the mass, g, and delta t. The values on the right require calculations and use of the tracker data to calculate. How each value was attained will be explained. T is the period of oscillation. This is the time interval for one complete oscillation. Using the lowest y points of the mass, we can calculate t. As seen in the tracker data, the lowest point in the corresponding time instance can be found by the red marks. These lowest points are also marked on the graph shown. I used the time at the third complete oscillation, subtracted it from the first instance of lowest point, and set it equal to 3t. Divided by 3 give the average period, which came to be 1.524 seconds. K is the spring constant. The spring constant is used in calculating the spring force. The period of oscillation for a spring mass system is given by the equation shown. We can algebraically manipulate this equation to solve for K. We are given the mass and we calculated T earlier, so plugging in the values we get K to be 6.836 newtons per meter. L0 is the relaxed length of the spring. This is used in calculating the difference of the spring's length at one instant and the relaxed length. Using observation of static equilibrium, which indicates that the net force is zero, we can find the relaxed length of the spring. Since net force is zero, this indicates that the magnitude of the spring force is equal to the magnitude of the weight force. Plugging in the corresponding equations and solving for L0, we get this equation. Mass is given to us, and K was solved for earlier. L is given to us in the lecture video as an instance where the spring was stretched. This value is 0.70 meters, as shown in the picture. Plugging in all the values, we find L0 to be 0.124 meters. This part of the code displays the equations of kinetic energy, gravitational potential energy, and spring potential energy. These are used in constructing the energy change graph that was shown earlier. This next part of the code updates the velocity and position of the mass using net force. Net force is calculated using the sum of weight force and spring force. You can see where in the code the equations are translated. This clip here shows the model constructed when the code is ran. You can see the motion of the mass represented by the blue ball. The motion of the blue ball is the predicted motion. The blue arrow represents the spring force and the black arrow represents the weight force. The red ball represents the motion of the original mass from the video. Its movement isn't so smooth because the time between each observed position is 20 times longer than the time between each predicted position. Here are the two computational models shown once again. In the first graph, while the predicted model follows the general motion of the observed model, there are clear disparities. This could be due to numerous reasons. It could be due to not accurately pointing the exact center of mass when analyzing the video and tracker, or it could be due to not factoring in forces such as drag force. For this model, the energy principle is almost satisfied. While the change in total energy plot shown by the yellow plot is very close to zero, it is not exactly zero as the energy principle would state. We defined our system to be the ball, spring, and earth, so there is nothing in the surroundings. This would indicate no energy transfers, which would mean the change in total energy is zero. However, it is not exactly zero because we did not account for forces such as air resistance. It could also be because delta t was too big. The period of oscillation from the x position data and from the y position data are shown here. The two periods are different because of an asymmetry in forces in the x direction and the y direction. In the y direction, there is the force of gravity that is accounted for.